Welcome to NPTEL online course on Fractals and Multifractals. In the last lecture, we have defined fractal dimension of any compact set of a given complete metric space. In this lecture, we are going to discuss how to estimate the fractal dimension for the given set. So, what we discussed in the last class, let A is a compact set belongs to H of x. Here H of x comma d is a metric space. We are assuming this is a complete metric space, but this result is true for any metric space. Here H of x is a non-empty compact subset of x, non-empty compact subset of x. For each epsilon belongs to 0, let n of a comma epsilon denote the number of the minimum number of closed ball of radius epsilon is needed to cover the set. A is denoted as n of a comma epsilon. If for the given epsilon and this n of a comma epsilon, if this limit exists for this quantity, then this d we can call it as the fractal dimension of A. We use the notation d of A to mention that A has a fractal dimension d. So, we already discussed that A is a compact set in the x, therefore, it has a existence of this such a n of a comma epsilon. As we mentioned, the covering of A, that means we are covering the set A by the balls of x n of epsilon, where n equal to 1 to m cap, closed balls we are covering. That means this is a subset of this cover. Now, if you are taking x1, x2, x3 up to m cap, that is the finite closed cover, that means B of x n comma epsilon is defined as set of all y belongs to S such that distance between x n comma y is less than or equal to epsilon. The closed balls is required to cover A. One can understand, if you are fixing the alpha, then we can get one cover which covers the A. By varying different epsilon, not alpha, epsilon, one can get the different covering for the A. So, we need to take the limit epsilon tends to 0 to find the finer cover of A, then thereby we are finding the number of boxes, that means number of closed balls with the radius epsilon we are finding. Now, while computing the fractal dimension of A, what is the difficulties? The epsilon is an arbitrary number, arbitrary positive number. In the theoretical computation it is fine, whereas in the practical computations, how to choose this epsilon? This is the arbitrary positive number. How to choose and how to get this number d, it is challenging. Now, this theorem elucidates how to fix the epsilon and how to estimate the box counting and fractal dimension of the given set A. Here A belongs to H of x, where H comma d is the metric space. Here you can see epsilon we are choosing like this one, epsilon n equal to C r power n, where r is the number lies between 0 and 1 and C is any positive constant, C is any positive constant. Now, one can observe that you can find this as a sequence epsilon 1, epsilon 2 up to epsilon n. One can get the geometric series C of r power 1 plus C of r power 2, C of r power 3 and so on. This geometric series convergence obviously when modulus of r less than 1. So, we can find the convergence point of this sequence by, instead of choosing the arbitrary epsilon greater than 0, if you are choosing the epsilon as in the sequence, this nice sequence, one can estimate the fractal dimension which is equal to our definitions. So, in this way one can find the fractal dimension of the given set A. Then if limit n tends to infinity, the closed balls we are taking in the sequence, this sequence here r value is less than 1, obviously this sequence is converging. So, this sequence of point we can find the number of closed balls is required to take this one, then this limit is converging, that limit we can call it as the fractal dimension of the set A. Let us prove this theorem. For proving this theorem, first let the real number r and c and the sequence of number E is epsilon 1 where n equal to 1, 2, 3 etc. be as defined in the statement of the theorem. The r is 0, 1 and c is the positive number and the epsilon n is defined at c r power n. Then this f of epsilon is defined as the maximum of epsilon n belongs to this sequence E such that this epsilon n must be less than epsilon. For the given epsilon, this epsilon n must be less than epsilon. Then assume that this epsilon is less than r, where r is lies between 0 and 1, assume that this epsilon is less than r. Then one can get f of epsilon is maximum among this epsilon n, this epsilon n is less than epsilon. Therefore, this epsilon n is less than epsilon, this epsilon is less than r. Therefore, maximum among this epsilon n is less than or equal to this epsilon. So, maximum among this epsilon n is less than the epsilon, and which is less than or equal to f of epsilon over r. This is a less than 1, you can denote this r is less than 1, this is less than f of epsilon is less than or equal to epsilon. When you are divided by this r, this quantity is greater than this term. If this is in the increasing order, f of epsilon is less than or equal to epsilon, then the number of boxes needed to cover the set A with respect to this radius is greater than the number of boxes is required to cover the set A with the radius epsilon. If you are comparing, this will is the greatest one. That means the number of, you can find the number of boxes needed to cover the set A with the radius f of epsilon, and find the number of boxes close to, boxes means close to balls, is required to cover the A with the radius epsilon. Now, the f of epsilon is less than the epsilon. Therefore, one can understand that the number of boxes will increase. For example, if you are taking closed interval 0, 1, if you are taking epsilon as 1 by 2, then these two boxes 0, 1 by 2, this is the closed ball, union 1 by 2, 1 is enough to cover the closed interval 0, 1. If you are taking epsilon equal to 1 by 4, then this closed interval 0, 1 is contained in 0, 1 by 4 union 1 by 4, 1 by 2 union 1 by 2, 3 by 4 union 3 by 4 comma 1. Now here the number of closed ball required to cover the set A with the epsilon 1 by 2 is 2, whereas here the number of closed balls of radius 1 by 4 is required to cover the set 0 comma 1 by 1 is 1, 2, 3, 4. One can understand here 1 by 4 is less than the 1 by 2. If the radius is less, that means you are covering this box 0 comma 1 by the smaller box of radius 1 by 2, you are getting 2, here it is 4. If your radius is less, the number of boxes will increase to cover the whole, that is apply here. Therefore, the number of boxes required to cover A with the radius f of epsilon is greater than the number of boxes required to cover the A with the closed ball of radius epsilon is this one. Similarly, this epsilon is less than or equal to f of alpha by r. Therefore, number of boxes required to cover A with this radius is greater than the with this radius. Now, since ln n is an increasing positive function of x for x greater than or equal to 1, this is the log curve with 1. After this is here like this one, then it is like goes this one. So, when x greater than or equal to 1, the log function is increasing positive function of x for x greater than or equal to 1. It follows that if you are taking logarithmic of log of a of epsilon by r, this one, for this one if you are taking the logarithm over log of 1 by this radius 1 over f of epsilon is less than or equal to log of n of a by epsilon over 1 by epsilon less than or equal to log of n of a f of epsilon by log of r over f of epsilon. So, if you are dividing this number by this one, you can get this quantity. Now, from here assume that this term tends to infinity as epsilon tends to 0. Obviously, whenever the number of boxes size is reduced to 0, then this term will increase. If not, then the theorem is true. If this is not true, this is fixed number, the theorem is true. Then consider the left hand side of equation 1. The left hand side, you can see this limit epsilon tends to 0, log of n of a f of epsilon over log of r over f of epsilon equals limit n tends to infinity. This one I am taking as instead of f of epsilon, because f of epsilon we are defining as this sequence maximum, you can replace by instead of f of epsilon one can raise epsilon n and here also epsilon n. Then this equivalently this term can equivalently written as ln of r over f of epsilon. This one can be equivalently written as the numerator is same, the denominator is ln of r minus ln of epsilon n. Then this can be written as ln of r plus this one you can take as the power ln of epsilon power minus 1. Therefore, it becomes ln of r plus ln of 1 by epsilon n. This time one can get. Now, this r is the constant number, ln of r is the constant number. Then this becomes limit n tends to infinity. This sequence, this will equal to this sequence. Now, you can say this is the right hand side of the equation 1. Now, you can check the left hand side of the equation 1. For we are checking this side. Now, one can check this side. This side is over. Now we can check this side. The limit epsilon tends to 0, the left hand side of the equation 1, ln of n of a comma f of epsilon over r over ln of 1 of f of epsilon equals. So this quantity I am writing epsilon n minus 1 over this quantity 1 over 1 minus epsilon, then which is equal to not epsilon 1, this is epsilon only, not an epsilon minus 1 epsilon. Now this quantity one can write limit n tends to infinity ln of n of epsilon n over ln of 1 over epsilon n. Then compare this quantity and this quantity. Here this side is convergence to one limit and this time is convergence to other limit. What is this one? Limit n epsilon tends to 0, this one ln of n of a comma epsilon over ln of 1 over epsilon, which is less than or equal to limit epsilon tend to 0 this term and greater than or equal to limit epsilon tends to 0 this quantity. Now this left side and right side both are convergence to this term, this quantity. As per the Squeeze lemma in the real analysis, one can get as epsilon tends to 0, both the left side and the right side hand side of the equation 1 approach the same value, claim in the theorem by the sandwich theorem of the calculus. Then limit epsilon tends to 0 of the quantity in the middle one also exists, this one also exists, which is equal to the limit of the both the sequence. Therefore one can conclude that limit epsilon tends to 0 ln n of a comma epsilon over ln of 1 over epsilon, which is equal to limit n tends to infinity ln of n of a comma epsilon n over ln of 1 by epsilon n. So the left side limit is this one, then right side is this one, therefore this one equal to this one. So now instead of finding the box counting dimension of A by using this formula for arbitrary epsilon, we can use the sequence like this one. Now we can use this one. So now the closed ball of radius we can choose from this sequence, then you can find the cover of A, then one can find the fractal dimension of that object. Now let us discuss the example to compute the box counting dimension of the object. Now as I mentioned, A is a compact subset of a metric space, it need not be a fractal. So for any set we can find the fractal dimension. Let us try to find the fractal dimension for any compact set in the R. So let us take A equal to 0, 1 in the R. R is our metric space. R is our metric space with Euclidean metric. One can consider from this metric space we are taking the compact set closed interval 0, 1. We verify the using the above theorem with a geometric sequence. So choose the sequence epsilon n equal to r power n. Instead of epsilon greater than 0, epsilon is an arbitrary number, we are choosing the epsilon in the sequence r power n and take c equal to 1, the arbitrary constant. Anything greater than 0 we can take as 1 for simplicity, where other number also we can take, but I am taking c equal to 1. Then to cover 0, 1 with the interval of radius alpha n, the number of boxes is required to cover the interval 0, 1 with the radius epsilon n is indirectionally proportional to 1 by 2 power epsilon n. How you can take 0, 1 here, 0, 1. We are covering the 0 comma 1 by the epsilon n radius. That means, what do you mean by the epsilon n? Epsilon n is the closed ball x comma epsilon n equal to set of all y belongs to x such that, in our case x is a real number, y such that distance between x and y must be less than or equal to epsilon n. Now, how we are choosing this one? That means the metric is modulus minus x minus y must be less than or equal to epsilon n. Therefore, that y must be lies between x minus epsilon n and x plus epsilon n for all the y is belongs to this interval. So, what is the length of this interval? One can find the, so by using this epsilon n and this we can find the closed interval like this one. By using the closed interval we can cover the boxes, that means this closed interval 0 comma 1, then the length of this interval is x plus epsilon n minus x plus epsilon n. So, this will cancel, one can get 2 power epsilon n. So, whenever this one approaches to 0, the number of boxes will increases. Whenever this epsilon n decreasing, this will increase, so that this is indirectionally proportional to 1 by 2 power epsilon n. Now, take the logarithm of both sides. So, log of n of 0 comma 1 epsilon n, one can write log of this one, then log of this quantity can be written as log of 1 over log of this one can be log of 1, a by b can be written as log of 1 by 2 time log of 1 by epsilon n, log of epsilon n. This can be written as log of a plus log of b, log of 1 by 2 plus ln of 1 by epsilon by n. Now, we can get this quantity. Now, take the ratio between this one and this quantity 1 by epsilon n. So, ln of 0 comma 1, the number of boxes required to cover the interval 0 comma 1 over epsilon n over ln of 1 over epsilon n, because we are in the sequence, we are choosing this sequence. Now, this term we can write like this one, and 1 by 1 over 1 by epsilon 1. Then if you are finding this one, this term will cancel, this term will cancel. That means, if you are separating this one, this term and this term will cancel, one can get this term ln of 1 by 2 by ln of 1 over epsilon n. So, this term you will get ln of 1 by 2 over ln of 1 over epsilon n. Observe that epsilon n we can take r power n. Epsilon n is r power n, or we are taking in the interval 0 and 1. Here, if n tends to infinity, this term r power n, if n tends to infinity, this sequence approaches to 0, because if you are taking 0.5, for example, r as 0.5, 0.5 power 1 is greater than 0.5 power 2. This is the decreasing sequence bounded by 0, because the bounded below by 0, this convergence to the number 0. So, as n tends to infinity, epsilon n tends to 0. In that meanings, 1 over 1 by epsilon tends to 0. If the denominator tends to 0, then ln of 1 over 1 by n tends to infinity, because this will get larger and larger. Therefore, if this is larger and larger, the ln of this large one diverges to infinity. That means, if this is infinity, then the denominator goes to infinity, then this term goes to 0. If this term goes to 0, one can observe, if this term goes to 0, then limit n tends to infinity, ln of 1 comma epsilon n over ln of 1 by epsilon n equal to 1. How we obtained this one? You can see this term tends to by 2, this term tends to 0, then the box counting the fractal dimension of closed interval 0, one can get this quantity 1. So, if this quantity tends to 0, then this can be written as ln of 1 over epsilon n over ln of 1 over epsilon n plus ln of 1 by 2 over ln of 1 over epsilon n. Now, from here this quantity tends to 0, that means this quantity equal to 0, then this quantity equal to 1. So, that this quantity, if limit n tends to infinity, so this term converges to 1. So, the fractal dimension of closed interval 0 comma is 1. Now, let us find the fractal dimension of middle third Cantor set, which we discussed in our previous class. Now, let us find the fractal dimension of the Cantor set. So, we find the fractal dimension of the closed interval 0 comma 1, that fractal dimension d of this one is 1. Now, we will find the fractal dimension of the Cantor set, we will find. Now, we know how we constructed the Cantor set. We are dividing the closed interval 0 comma 1 and 3 equal part and removing the mid open interval, and we will get in the after first iteration we will get this type of set, union of these two we will get, and after that this will divide into 3 equal part. We need to remove the middle, we need to divide this interval as a 3 equal part and remove the middle, then we will get the after second iteration one can get union of this one. So, understand, after each iteration there are 2 power n interval is producing with the length of 3 power n. So, that means after the nth iteration one can get 2 power n number of interval, each of their size is 1 by 3 power n. Here the only one interval of length 1, here there are 2 interval of length 1 by 3, here there are 4 interval, that means 2 power 2 interval of length 1 by 9, that means 3 power 2. So, after nth interval we will get this one. So, at the stage n, the set consisting of 2 power n interval, each of its length is 1 by 3 power n. Now, this I am taking as an epsilon n. So, how we need to change the epsilon n? Epsilon n must be C r power n. The C must be greater than 0 and r is lies between 0 and 1. Now, 1 by 3 is lies between 0 and 1. Now, we are fixing epsilon as 1 by 3 power n as per our theorem. Now, for each interval can be covered by the one set of size epsilon n. For example, after the first iteration we will get this is 0 comma 1, and after the first iteration we will get 0 comma 1 by 3 and 2 by 3 comma 1. So, after the first iteration we are getting 2 sets. If you are taking n equal to 1, then if you are fixing epsilon equal to 1 by 3, so each interval can be covered by one set of size epsilon 1. So, this set is covered by 1 by 3 radius closed ball. The closed ball is 0 comma 1 by 3, and here also this 2 by 3 comma 1 can be covered by the interval closed interval 2 by 3 comma 1. Here the radius of this closed ball is 1 by 3. So, in each nth interval, if you are taking a nth interval, if you are fixing epsilon n as 1 by 3 power n, then the 2 power n number of closed balls covers the, here there are 2 closed balls is required. In the nth step, 2 power n number of balls of radius epsilon n given here will cover the Cantor set in each state. Now, we need to take the, as per the definition, now limit n tends to infinity, logarithm of n of a comma epsilon n over ln of 1 over epsilon n. One can find the fractal dimension. Here what is the epsilon n is 1 by 3 power n and n of a comma epsilon n is 2 power n. So, if you are taking the logarithm, one can get this quantity as the numerator as n times ln 2 limit n tends to infinity, one can get n times ln 2. The denominator is n times ln 3. Now, n will cancel. So, we will get ln 2 by ln 3 that we can here. So, if you are taking the ratio between the two number, one can get ln 2 by ln 3. So, here it does not depends on the iteration, this does not depends on the n, therefore, n limit n tends to infinity, this quantity equals to ln 2 by ln 3, this is less than 1 and greater than 0, approximately 0.63 approximately. Now, one can observe we obtained the fractal dimension of closed interval 0 comma 1 and which is equal to 1. Now, we obtained the fractal dimension of the Cantor set C which is equal to ln 2 by ln 3. Here one more important thing is with respect to the any iteration, if you find the dimension of the Cantor set, you will get ln 2 by ln 3, it is invariant. It is an invariant. If you compare this quantity, ln 2 by ln 3 is less than the 1. That means, the dimension of the Cantor set is less than the dimension of the embedded space 0 comma 1. So, Professor Benoit B. Mendelbrod defined the fractal in two ways as I explained while starting the multifractality concept. One way is based on the self similar property, whether it is if object has the self similar property at arbitrary all the scale, then it is called the fractal object. That means, every corner the object exhibit the same nature. If this property is satisfied, we can call it as a object as a fractal object. Alternatively, one can find the topological dimension and the Hausdorff dimension of the object. If the Hausdorff dimension is strictly greater than the topological dimension, it is called as the fractal object. Now, I have discussed one more equivalent definition. If C is a object which is embedded in the interval 0 comma 1 here. Now, if you are finding the fractal dimension of C and the fractal dimension of closed interval 0 comma 1, if the fractal dimension of C is lesser than the fractal dimension of the embedded space, then we can call it as C as a fractal. Now, the Cantor set we already proved that it is a fractal. This dimension theory by obtaining this way also ensure that C is a fractal, and also this quantity 0.63 says that how much this Cantor set is dense in the set 0 comma 1. That means, how much the Cantor set is distributed in the set 0 comma 1, because C is embedded in 0 comma 1. So, what is the advantage of this method, this theorem? One can find can go to the theorem here. So, advantage of this theorem is, instead of choosing the epsilon as arbitrary epsilon, if you choose the epsilon in the geometric sequence, then one can find the fractal dimension of the object. For the practical computation, if you are choosing this sequence to find the fractal dimension, it is easy way. In the two object here A equal to 0 comma 1 and the Cantor set, we have choose this type of geometric sequence, and we obtained the fractal dimension of both the set closed interval 0 comma 1 and the Cantor set 0 comma 1. Here it is the reference for this concept. Thank you.